Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Applied Thermodynamics, Module 4 Gas Turbine Engines. So, in previous lectures, we analyzed the gas turbine engine components, thermal circuits, gas turbine performance cycle part 1. Now, we are going to discuss about gas turbine performance cycle part 2. Here we will mainly discuss about the modifications of basic cycles in order to improve the performance. So, you are in the lecture number 3. So, under this lecture following topics will be discussed, that is modifications to basic cycles. What are they? First we will discuss about a intercooling cycle, we will discuss about a reheat cycle, and these two cycles are introduced in the basic cycles with a main intention to increase the work ratio or work output. Other one which we discussed about this heat exchange cycle. So, this is also a part of this basic cycle, but this particular cycle can be also integrated with intercooled and reheat cycle. So, that it will also ensure the efficiency. So, meaning that reheat with heat exchange or intercooling at heat exchange has the potential to improve the power output as well as the cycle efficiency, and that things comes under the combined performance. Just to give the brief introduction about the what the basic cycles with what we discussed, the simple gas turbine or Brayton cycle has 1-2 isentropic process, 2-3 constant pressure process where heat is added, 3-4 isentropic expansion process in the turbine, and 4-1 constant pressure heat rejection process. So, similarly, what you show is in the PV diagrams as well as in the TS diagram the cyclic process. And for this basic cycle we defined the efficiency as a function of pressure ratio and the gamma, and also we find the net work output from this cycle, and these two are the main factor for analysis. So, what we observed is that the work ratio and cycle efficiency are very low in the basic cycles. They can be improved by increasing the isentropic efficiency of the compressor and turbine with proper blade design in the manufacturing process. So, basically first thing is that one thing is that we have to make the thermodynamic process in the compressor and turbine to follow more and more isentropic nature, but that has also any limitations. So, because the practical cycles are associated with irreversibilities, and second issue is that the upper limit of the cycle temperature is fixed based on the materials used in the turbine blades, and of course, in the compressor side there is a limiting case that we cannot go beyond certain pressure ratio because handling will be difficult, and while we are going for very high pressure ratio within the compressor in a single compressor, then it becomes non isentropic in nature. So, these are the some of the issues that needs to be attended, so that we get a better cycle efficiency and work power output. And then another topic of interest which we discussed in the last class is that the specific power or power output and cycle efficiency, they are functions of pressure ratio as well as the temperature ratio. So, when you are increasing the pressure ratio, obviously cycle efficiency increases beyond some point and it comes down, but at the same time when you increase the temperature ratio, we can have a prolonged cycle efficiency for a wide range of pressure ratio. And these are the some of the things that there are some limiting temperature and pressure ratio range a gas turbine cycle needs to be operated, and this has been proven that the cycle efficiency as well as work output are related to temperature ratio as well as the pressure ratio, and for a given power output or for given applications, the temperature and pressure ratio is fixed for a particular application. Now, having said this, let us see that how we can improve the performance. So, considering the temperature ratio and pressure ratio as the vital parameters, we have to see that how we can adopt certain methodology in which we can improve the performance. So, by improving performance means we mean two things. First thing, power output needs to be increased. Second thing is that cycle efficiency needs to be also increased. But as far as the cycle efficiency is concerned, because the gas turbine engines many times we are mainly concerned with work ratio, because that is the things power output requirement fixed by the user. To having said this, that having that work ratio with us, then you have to see what cycle efficiency we are going to get. So, for that reasons there are some adaptable or possible methods that are introduced. First thing is intercooling between compressor stages and reheating between turbine stages. So, these two are things that basically speaking, that to increase the work ratio we need to either increase the work output from the turbine side. So, that can be done by through reheating. Other way is that we can reduce the compressor work. So, that can be done through intercooling. So, these two things will give you higher work ratio. But at the same time, if you are very concerned about the efficiency, then we have to think about the combination intercooling and reheating combination with a heat exchanger. But when you adopt this third method, that intercooling and as well as reheating, so in both the cases we are going to get the power work output or power ratio high, but the cycle efficiency we cannot guarantee, it may drop. To have the conditions that we must also increase the cycle efficiency, if we are very concerned with that, then this intercooling and reheating should be adopted with a heat exchanger cycle or heat exchange cycle. So, these two things are these four things are basically very vital for the design of a gas turbine power plant. And when you look at, and this is mainly used when we have a shaft power cycle, but in aircraft practice we expect the thrust. So, life expectancy of the engine is shorter, hence the maximum temperature is higher in the industrial gas turbine unit. So, your main intention is the maximum high temperature, and there, since they are thrust specifics, the concept of high work ratio is not feasible. That means, since you are not concerned with high work ratio, so intercooling and reheating concept is not part of the aircraft cycles. So, their aspect is something different, for that we will see later. So, these two plots which we have shown in our last class, that how a specific work output and efficiency varies with pressure ratio as well as the temperature ratio. Now, let us start with the first modification, that is what we call as a intercooling cycle. So, it has been shown that in thermodynamics, that when you make this compression process in a quasi static manner, you will consume less work. So, in that sense, instead of going for a single stage compression, intercooling method is adopted. So, in that way, when we are doing this compression is performed in multiple stages, 2 or more stages, the work input will be reduced. So, for that an intercooling is introduced. Now, what does this intercooling does? This brings down the temperature of air to the inlet temperatures. So, it can be shown that work input with intercooling is less than the work input with no intercooling. So, hence when it is assumed isentropic efficiency between two compressors, each equal to isentropic efficiency of a single compressor if no intercooling is adopted. So, it means that if you are using the intercooling methods and assume same isentropic compressor for each things, then with this intercooling method your work input will be reduced when you do go for a multi-stage intercooling or 2 or more compressors. And this is mainly because if you recall this TS diagram. So, in the beginning part TS diagram, the width between the pressure ratio is less and it diverges as and when we go as and when the pressure ratio increases. So, it means that when you are in the compression side this difference is smaller, but in the expansion side this difference is larger. So, that is the basically by looking at the trends of the diagram and taking the advantage of this TH diagram, people we used to use the concept of intercooling and reheating. Now, let us see that how an intercooling cycle operates. So, here what has been given is that here we have two compressors, low pressure compressor, high pressure compressor, and they are coupled with the turbines and entire power comes from the turbine for both the compressors. And there is an intercooler between 2 to 3. So, the ideal cycle goes in the sense that if the cycle, suppose if the cycle starts with 1, from 1 if it is a ideal isentropic cycle, then it will have 1 AS 5 and 6S. If it is an non isentropic cycle without intercooler, it will be 1 A 5 6. So, this would have been the case when it is a simple cycle. Now, with intercooling what does it do? That the by after the first stage of compression, that means at 2 or 2s, the cycle cycle temperature is again brought back to the original temperature, and then further second stage compression starts from that. So, this process now becomes 1, 2, 3, 4. So, it is like 1, 2, 3 and 4, and at the process mean isentropic, it would have been 1 2s in the first compression or 3 4s in the second compressor, and finally, the circuit goes like this. So, this is how the TS diagram explains the intercooling arrangement or circuit arrangement. Now, there are some other factors that plays that when you will deal with the compressor in the last module, we will find out that the best intercooling pressure is the one which gives the equal pressure ratio at each stage of the compression. So, the work output is a minimum when the pressure ratio at each stage is same. That means, the pressure ratio in each stage remains same. If you have n number of stages, the pressure ratio in each stage should be equal in each stage. Then only we call this as a perfect intercooling. Since the compressor and work input is reduced, work ratio is increased, that is what we explained already. The heat input requirement is increased when the intercooling is used. So, this is another drawback for intercooling, that your input heat requirement is increased because you need another intercooling circuit. Although the net work output increases by intercooling, but it is found that cycle efficiency drops in the most of the cases due to increased heat supply, because we need some kind of circuit that takes out this heat from the compressed air. So, we need an intercooler circuit. So, that means you need another additional device that must take this heat. And of course, in many times if the intercooling arrangement becomes bulky, and it becomes a disadvantage in terms of work ratio. So, these are the some drawbacks, but intercooling is one of the options to reduce the compressor work. Now, let us see that how an intercooling cycle mathematically proves that work ratio is increased and cycle efficiency drops. So, this we can see here, that you let us take the circuit that with an intercooling circuit, the work output can be divided into work input would be W12 plus W34. That means W1 to 2, that is process 1 to 2 plus W3 to 4. That means these are the two circuits that consumes work. So, you can write it as a Cp times T2 minus T1 by looking at the temperatures and C plus Cp times T4 minus T3. Now, had this process been without intercooling, then the work input would have been like this, that is Cp times Ta minus T1. So, you can rewrite this expression as Cp times T2 minus T1 plus Cp into Ta minus T2. So, by analyzing these two expressions, one can clearly say that with this and looking at the number here, we can see that this with intercooling the work input is less, and this minimum work with intercooling is possible. That means, this work is minimum work when the pressure ratio in each stage are equal. So, when the pressure ratio is each stage equal, that means this we are after each stage of heat compression, the temperature must be brought back to its original temperature, that means T3 must be equal to T1. So, an ideal circuit would be that after the first stage of compression, the temperature should be brought back to its original temperature, that means T3 and T1 should be equal. This is how what we say that with intercooling what happens to work. Now let us see with intercooling what happens to heat. So, when you say heat, so with intercooling we can write this as Cp times T5 minus T4, and with no intercooling we can write it as Cp into T5 minus Ta. And one can clearly say that with intercooling the heat input is increased. So, when heat input is increased, and now what will happen is finally work ratio, obviously the compression work is reduced. So, work ratio is increased because you are not touching the turbine work. But in other side of the story is that when you see this the cycle efficiency, there is a chance that with because since Q in is increased, cycle efficiency may likely drop out. Of course, all it depends on the value of W net, and in most of the situations the cycle efficiency generally drops. Now, let us see what happens to reheat cycle. So, this is some completely opposite phenomena. So, in the opposite phenomena what happens is that do not touch anything about the compressor, you think about what best you can do to increase the power output from the turbine. So, for that reason the turbine stages are divided. So, one is called as high pressure stage, other is the low pressure stage. So, this high pressure turbine now drives the compressor, and the low pressure turbine is now separate to give that gives the power output. Now, if you look at this thermodynamic TS diagrams, so the compression process 1 2s or 1 2 remains as it is, but in the expansion process it is now goes at the in the 2 stage, that is from 3 to 4 in the high pressure turbine expansion, and then again reheated, that is 4 to 5 through another combustion chamber, again 5 to 6 is another expansion in the low pressure turbine. So, the process now becomes 1 2 3 4 5 and 6, and had this process been a complete single stage expansion, then the process would have come from 3 to A. So, this would have been the case 3 to A, now it has gone to other 1 3 4 5 6. Again when you do the reheating, the reheating has to take place till the maximum temperature. So, the reheat process is very, we say complete, then when you T3 becomes T5, normally reheating takes place till we get the upper limit of the temperature, that is typically T3. And in the process of this reheating, what we get, the expansion work is increased, but since the compression work remains on stage, so the work ratio is always higher, but the additional heat is supplied in the combustion chamber. So, the combined effect is to reduce the thermal efficiency. The exhaust temperature of the gas leaving the LP turbine is higher when the reheat is used. So, hence the heat exchanger can be used to enable some energy from the exhaust gas. So, what it happens is that, so when we are doing reheating, obviously we are going to go for very high temperature, and finally when the exhaust goes out, instead of releasing it to the atmosphere, then we have to tap that heat. So, normally to tap that heat we require a heat exchanger, but that is a separate aspect, we are not going to, we will discuss about that part later, that how we can better I can manage in a better way from the taking the exhaust from the turbine. So, that is a separate aspect. Now, let us see that how reheat improves the work ratio and what happens to cycle efficiency. So, this phenomena is something a reverse phenomena. So, let us think about low pressure turbine with reheating. So, when you have a low pressure turbine, the net work becomes, because here the power output has two parts. One is the actual power that we get is from low pressure turbine, and the high pressure turbine normally drives the compressor. So, that means turbine work is equal to compressor work, and this can be written as Cp times T2 minus T1 is equal to Cp times Cpg into T3 minus T4. So, here you will see that when you look at the compressor side, it is mainly air. Now, when you say turbine side, it is the hot gas. So, that is what Cpg has been written. So, it is a hot gas, because we have already fuel and air mixture. So, Cp would have changed, and that is T3 minus T4. Now, if you can look at this particular figure, we can write that Cpg, suppose you do the reheating in the so LP turbine with no heat reheating is okay. So, let us start with HP turbine with reheating, it is Cpg into T5 minus T6, and when you say LP turbine with no reheat, then it will be Cp times W net would be Cpg into T4 minus Ta. And now, similarly for HP turbine we can get the compression work, but finally what it matters is the net work due to reheat, and this we can find out had the process been without reheating and with reheating in a LP turbine. So, it can clearly say that this particular number Cpg T5 minus T6 is always greater than Cpg T4 minus Ta. And in this process of reheating, how much heat extra heat we are going to add. So, this can be given because from 4 to 5 it is going again. So, so this in this 4 to 5 process we are adding extra heat in the combustion chamber 2. So, that is the reason we can say the extra heat that gets added is Cpg times T5 minus T4, and how much heat we are going to supply without reheat, then it would have been Cpg T3 minus T2. So, if there is no reheating, so it would be T3 minus T2, and in this way we can clearly say that through this reheating process your turbine net work is higher and cycle efficiency drops, because with reheat we are adding extra heat, and since Q in becomes higher, so cycle efficiency drops. So, this is the disadvantage of reheat cycle. And some extra philosophy we can say that with reheating in the TS diagram. So, the extra when the TS diagram normally represent area under TS diagram is extra heat additions. Now, in that case, if the extra heat added in the cycle becomes 4, 5, 6 and 4 dash. So, this particular extra heat since gets added, which we have shown that because of this reason cycle efficiency drops. So, this is again another way of representing the things, and some better inferences that we can draw, that substantial increase in the specific work output can be obtained by splitting the expansion and reheating of the gas between high and low pressure turbines. So, because of this turbine work increases, because since the vertical distance increases with increase in the entropy in a TS diagram, because this particular gap, as you go further in the TS diagram, this part diverges. Since this part diverges, So, we can say that turbine work increases because the vertical work increases. The cycle efficiency drops with addition of extra heat in the cycle, and assuming that gas is reheated to the, and this reheating process is optimum when these T5 and T3 are equal. That means reheating has to take place to the peak temperature, and work transfers for HP and LP turbines are equal. And the another way of representing the cycle efficiency, the way we represented for basic cycle and heat exchange cycle, we can also calculate for a reheat cycle what can be the expressions for non-dimensional work in terms of pressure and temperature ratio. So, those aspects you can see that the non-dimensional work can be represented in this manner: W by Cp times T1 is equal to twice T whole bracket 1 by 1 minus 1 by square root of C minus whole bracket C minus 1. So, this is how the with reheat, and with reheat the cycle efficiency can be expressed in terms of temperature ratio and pressure ratio. Okay. And it can be shown here that we have shown here three expressions. One is a reheat cycle efficiency, second is simple cycle, and third is a heat exchange cycle. So, it can be shown that for a reheat cycle efficiency is the least, and the heat exchange cycle the efficiency is the highest by looking at these expressions. Similarly, with for a reheat cycle, the W by the specific work is higher than the simple cycle. So, this has been shown in the proven and the mathematically that in a reheat cycle the specific work output is higher, but the efficiency drops. Now, we have already discussed some details about heat exchange cycle, but here the heat exchange cycle is analyzed with a context that the heat exchanger has to be an integrated part when you are talking about reheat or intercooling. So, now let us see that when you introduce a heat exchange cycle, where we can put it. So, the ideal location of a heat exchanger would be that from turbine outlet and till the exhaust, and similarly from the compressor outlet to the combustion chamber. So, in that process we are going to tap the extra heat that is available in the exhaust gas, and that can be utilized to preheat the air when it leaves from the compressor. So, in an ideal scenario, the air compressor would be heated from T2 to T3, that is equal to maximum of, it can be a maximum of T5, and gas from the turbine exit is cooled from T5 to T6, which as upper limit could be T2. So, if you look at this particular figure, this is an ideal scenario which, and available temperature available is the difference, that is T3 minus T2 or T5 minus T6, but actually what happens in a actual cycle, normally heating we cannot go up to the 0.5, we will land up at the 0.3, and while heating, and while the exhaust gas instead of getting cooled to temperature T2, it stops at 0.6. So, the location of 3 and 6 is the location where it is within the available temperature difference between T2 and T5. So, that is the reason we say that ideal location of heat exchanger is to tap the, with an intention is to tap the heat from the exhaust of the turbine. Some of the other inferences that can be drawn here, that required temperature difference between the gases and air entering the heat exchanger is T6 minus T2, while the required temperature difference of the gases and the air leaving the heat exchanger is T5 minus T3. So, the heat is lost from the heat exchanger to the atmosphere, then the heat given by the gas is exactly equal to the heat taken up by the air. So, the assumption of no heat loss from the heat exchanger is sufficiently accurate in the most of the cases irrespective of the temperature T3 and T6. So, and finally, when we heat exchanger is used, heat supplied in the combustion chamber is reduced assuming maximum temperature cycle temperature is unchanged. So, the net work output is remains unchanged, but the cycle efficiency is increased. And to get some assessment of mathematical assessment, we define a parameter called as a heat exchanger effectiveness, and it is defined to allow the temperature difference necessary for heat transfer or transfer of heat, that is ratio of heat received by the air to the maximum possible heat, which could be transferred from the gases in the heat exchanger. That means, we have available temperature difference. With that available temperature difference, we have certain quantity of maximum heat transfer possible, but due to our variety of regions, we are not going to tap the exact amount of that quantity of heat. So, to have certain kind of estimation, we define this heat effectiveness. So, a simple heat balance equation can be used, that is what is m dot a Cpa, that is T3 minus T2, that is the available temperature, but what the gas can give us, take these things, that is mg into Cpg into T5 minus T6. Here we can see that when we are looking at the turbine side, we are representing at the gas term mg Cpg, that is specific heat of the gas, and when we are looking at the compressor side, we look only for the air. And ideally, when we are m dot a, m dot g, and if you say there is no fuel is supplied, then this number m dot a and m dot d has no meaning. And in that context, there are two parameters are defined. One is effectiveness, which is nothing but the ratio of between these two, that is effectiveness of heat exchanger. And in some other situations, to make the analysis simplifier, we defined a parameter called as thermal ratio. Thermal ratio means, if you take that ratio m dot a Cpa divided by m dot g Cpd, if this ratio is unity or close to unity, then this instead of writing effectiveness, we simply write it as a thermal ratio, because effectiveness, because mass flow rate and Cpa value has no role onto it. So, the thermal ratio and effectiveness are equal when the thermal products of the gases have same value with that of air. So, it is also possible that we can say that heat exchanger cycle, how it can improve the cycle efficiency. So, a typical TS diagram is drawn here. So, from this we can say that for a heat exchange cycle, that is efficiency is defined by eta h is equal to T minus C by T, and this, by putting this, we can say this particular relations holds good, that is for a heat exchange cycle the efficiency is always higher. Of course, we are not touching the work output. Now, to give some kind of introduction to combined performance, of course, the circuit becomes too complicated when involves so many components. So, here a situation, another situation could be a cycle, could be with reheat and heat exchange. So, reheat means we will have a LP turbine, low pressure turbine and high pressure turbines. So, these two turbines can be part of that, and then a heat exchanger could be another part, that will have two, basically one primary unit will have a combustion chamber, secondary addition of heat would be a reheat chamber, and complete thermodynamic cycles could be 1, 2, then with reheating 2 to 7 it can go, and from 7 to 3 through the combustion chamber, then 3 to 4 that is in the low pressure turbine, that is expansion, then 4 to 5 in the reheat chamber, and 5 to 6 in the expansion in the second turbine, and 6 to 8 that goes till the exhaust, and from 8 to 1 and the 8 to 1 it is something like this particular loop, where it is actually open, but here it is closed in the sense the sum because the exhaust goes to atmosphere and from the atmosphere we get the fresh air. Now, in another way we can represent the cycle with reheat and heat exchange by in terms of efficiency and pressure ratio. So, when you say a simple cycle with heat exchange, so as I mentioned in my previous lecture, see, if you have only simple cycle, we can drop this dotted line curve, and here the efficiency is a function of pressure ratio. And when you look at these particular curves, these curves are shows that your efficiency is a function of temperature ratio as well as the pressure ratio. Now, these 2 points merge at or intersect some location, and those points are treated as the optimum things. Now, with this reheat concept, if you look at this with reheat also the pressure the basic curves is also going to change for different temperature ratio, and side by side with reheat and heat extraction cycles, these curves will somewhere, that means what we can say, with a very high temperature reheat cycle we can achieve a large pressure ratio. So, this is the very basic philosophy, and we can say, of course, this circuit becomes too complicated, but just to give that such a cycle is also thermodynamically possible. And finally, I can summarize whatever we have, that what we call as a combined performance. So, we have discussed so many ways that a circuit can be modified with an intention for work output or with an improvement of work output or efficiency. So, if you want to summarize that what as an user what we should do. So, the first thing is that improvement in the specific work output through intercooling is normally not recommended, because they are bulky, they need large quantities of cooling water in a typical gas turbine plant, although thermodynamically it is one of the very viable option to reduce the compressor work. Modifications to low temperature region in a cycle normally less significant. Normally what happens is that compressor is typically low temperature zone or cycle. In the cycle, the region of gas is in the low temperature regime when it is in the compressor side, and the gas is at high temperature regime when it is at turbine side. So, people do not make any alteration in the low pressure region. That means you need intercooling unnecessarily we are going to get, because when you deal with the low pressure, of course, it does not have a work capacity or heat capacity, sufficient heat capacity. So, there is no point in going significant modification. So, always for modifications are treated only in the high temperature region of the cycle. So, that is what reheat is a better approach than intercooling, first thing. Now, when reheating with intercooling increases the cycle efficiency. Now, when you say reheating, anyway we are going to go to reheat, and then we have to go for intercooling. Increases the cycle efficiency when a heat exchanger is incorporated. That means, a actual gas turbine cycle that involves reheat and intercooling must use a heat exchanger. This is what it means. But there are some situations where the choice of pressure ratio is a very vital, and it depends on whether the high efficiency or high work output is required. That means, whether you want a very work output means you require a small size, high work specific work means you need, whether you require a small size unit or large size unit. So, depending on the pressure ratio we can make a judgment. For cycles without heat exchange, higher pressure ratio should be used when there is a no heat exchange cycle is there. So, higher pressure ratio should be used to take the advantage of higher permissible turbine inlet temperature. So, all these things are true that involves all these significant summary can be used for the gas turbine cycle, and it is used for all practical cycles. Okay. So, this is all about the performance of gas turbine cycle. Now, we will try to solve a problem that involves it is a big long problem, but the entire idea is that here this problem will demonstrate that what we are going to discuss. So, the problem goes like this, that a gas turbine unit produces 4 megawatt power while operating at pressure ratio of 9, and it involves 2 compressors with intercooling in between stage. So, let us see the circuit first. So, first we have to draw the circuit, that means it is a compressor, 2 compressor with an intercooling in between, and the HP turbine is used to drive the compressor and LP turbine is used to drive the generator. So, there are 2, and this HP turbine is used to drive the compressor unit, whereas LP turbine is used to drive the generator, that means it is going to produce the power. Okay. So, that means these two shaft for these two are different. Okay. So, LP turbine and HP turbine shafts are different because one produces the power, other drives the compressor. The temperature of the gas entry to the HP turbine is 650 degree centigrade, and the gases are further reheated to the same temperature. The exhaust gases leaving the turbine are passed through an heat exchanger. So, obviously, when we have to, the exhaust gases has to pass through because we are going for reheating. So, it has to go, we have to have a heat exchanger here. The compressors have equal pressure ratio and intercooling is perfect. So, it is a perfect intercooling system, that means pressure ratio is in stage should be are equal. The air inlet temperature is 15 degree, the isentropic efficiency of the compressor as given and turbines are given, and for heat exchanger the thermal ratio is given, that means we do not bother about the heat capacity of gases as well as the air. So, thermal ratio is given. So, finally, what we are going to get is cycle efficiency, work ratio and mass flow rate. So, these are the numbers we are interested. So, let us see how we are going to solve it. To solve, the first step is to calculate temperatures. And if you look at the TS diagrams, one can draw the process in the TS diagram for the entire circuit 1, 2, because since the isentropic compressor efficiencies of the compressor and turbine is given. So, we have to do in that manner. So, the process goes from 1, 2, 3, 1, 2, 3, 4, 4, then 5 is till heat exchanger, then we have 6, then 7, then 8, 9. So, 6, 7, 8, 9. So, we will go step by step. So, the process 1 to 2. So, you can for the process 1 to 2 we can write down the compression stage. So, you can write down the relation, this isentropic compression T2s by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. Now, we know this P2 by P1 is equal to 9 square root of 9, because for each stage it is square root of 9. So, it is 3. So, T2s we can find out from this expression, since you know this, and gamma is 1.4 because we are looking at the compressor side. So, from this equation this will give you T2s as 394 Kelvin. So, once we know these things, so we know compressor efficiency, that is T2s minus T1 divided by T2 minus T1, and that efficiency is 0.8. So, this will give you the temperature T2, because T1 is 15 degree centigrade, that is 288 Kelvin. So, T2 will be 420.5. So, input this expression here, T2 would be this. Then and then we have to find out the from the compressor work. Compressor work can we find out WC would be Cp times T2 minus T1. Because this compressor work is required, that you know 1.005, why required? So, we already find out T2 420.5 minus T1 is 288. So, this number would be 133.1 kilojoule per kg. So, what we have given is that high pressure turbine drives the compressors. So, basically there are two compressors. So, turbine work would be 2 times the compressor work. So, twice WC. So, you can get the turbine work to 66.2 kilojoule per kg. So, now when you say turbine work we get, then let us come back to this part of the cycle, turbine side. So, from the turbine side we can write Cpg into T6 minus T7 is equal to 266.2. Okay. Now, what we know is T6. Okay. So, T6 is known to us 650 degree centigrade, and that 650 degree centigrade is nothing but 923 Kelvin, and Cpg, that is, since it is a hot gas, so we take 1.15 kilojoule per kg. So, this is a typical number when for hot gases in a gas turbine we can take this value, it is not equal to Cp of air. So, from this, once you know this, so this will give you T7, and T7 is nothing but will be 691.5 Kelvin. So, once you know T7, then we will go to HP side turbine. So, efficiency of HP turbine is T6 minus T7 divided by T6 minus T7s. So, that is equal to 0.85. So, we know T6, we know T7. So, this will give you T7s. T7s would be 650.7. Okay. Then once you know this T7, then we can recall the pressure ratio. That is P6 by P7 is equal to T6 by T7s for an isentropic process, gamma by gamma minus 1. Now, here the gamma you have to take as 1.33 because this is for hot gas. Okay. And this pressure ratio becomes P6 by P7, that is between these two, would be equal to 4.09. So, we already know T6 nothing but 650 923 Kelvin, and T7s we found out as 650.7 Kelvin, and gamma is 1.33. So, once you know this, then we can find out the reheating process, that is LP turbine, and that is P8 by P9, and this becomes 2.2, that is that we can how we are going to find out, that is 9 by 4.09, that is 2.2. Now, when you know P8 by P9, then we can rewrite this equation T8 by T9s is equal to P8 by P9 to the power gamma minus 1 by gamma. So, from this equation we can find out T9s is equal to T9s would be equal to 762.8 Kelvin, because we know this P8 by P9, T8 is nothing but T6, that is 923 Kelvin. So, we find out T9s. Okay. Once you do this, then T9s, then you have to find what is actual T9. So, for that we can write efficiency of low pressure turbine, that is T8 minus T9 divided by T8 minus T9s, and that is equal to 0.85, right. So, when you say this thing from this equation, we also know T8, we know T9s. So, T9 can be calculated and this value would be 786.8 Kelvin. And then for this is about we get all the temperatures. Now, let us now talk about these particular answers which we are looking at, the cycle efficiency, work ratio and mass flow rate. So, for low pressure turbine, that we can write Cp9 Cpg into T8 minus T9. So, low pressure turbine work we can calculate at 156.63 kilojoule per kg. Okay. So, this is actual work that we want to have. Then we have to recall this thermal ratio Tr, that is T5 minus T4 divided by T9 minus T4, that is by definition, and this value is 0.85. Then what we know here and what is your objective in doing this calculation, you have to calculate what is T5. So, this will give you T5 as 731.8 Kelvin, because we know T9 is 786.8 Kelvin, T4 is equal to T2, that is 420.5 Kelvin. So, we get T5. So, once we know T5, then we can calculate Q in. So, Q in has two parts. One is Cpg into T6 minus T5, T6 minus T5 plus Cpg T8 minus T7, and all these numbers we know. So, this then we can find out Q in as 486.1 Kelvin. So, in your earlier calculation we found T6 as 923, T5 already it is here, T8 is also 923 because 6 and 8 are same, T7 691.5. Okay. So, we get Q in, and in the last calculations we also get Wt, that is from low pressure turbine, that is 156.43 kilojoule per kg. So, here it is kilojoule per kg Q in. So, cycle efficiency we can find out, first part W net by Q in, and this ratio will give you 156.43 divided by 486.1. This is will give you 0.322. So it is 32.2% efficiency. And the next part, the work ratio. So WR we can write as W net by W turbine. So W turbine has two parts. One is this LP turbine and this part. For LP turbine we get this. For WT HP turbine, what we get from the beginning, it was 266.2 kilojoule per kg. So this becomes 156.43 divided by 422.83. So this is nothing but summation of these two, and so that WR becomes 0.3635. So we get this work ratio 0.3635. And last part is mass flow rate. So mass flow rate, for the mass flow rate we require 4 megawatt. So m dot, that is part C, m dot can be calculated as 4000, that is total power kilojoule per second, divided by how much power we are getting, 156.43 kilojoule per kg. So this ratio will give you the mass flow rate as 25.5 kg per second. Okay. So of course, if you look at this particular problem, the problem is very big, but the simplified way of analyzing it is to draw the TS diagram, calculate the cardinal temperatures, then use this expression how much is getting added. So accordingly, in overall sense we can get the cycle efficiency, work ratio and mass flow rate. These are the point of interest. Okay. So with this I conclude this particular part, that is gas turbine performance cycle part B. Thank you for your attention.